Welcome in the world of artificial intelligence under artificial intelligence using Python series of lectures. This is lecture on randomized search method part 3. Hi, I am Dr. Sunil from GCS Solutions. The contents of this lecture are, we'll see the random walk algorithm and after that we'll try to analyze the random walk algorithm. The iterated hill climbing algorithm randomly selects different starting points with the intention that at least one of the solutions from the starting point will be a global optima. And this iterated hill climbing algorithm we have already seen in the earlier lecture. Now this iterated hill climbing is partially random in nature, but the random walk algorithm on the other hand is completely random in nature and it randomly selects the starting point in each step of each iteration without bothering of the gradient. We'll see this how this random walk algorithm randomly selects starting point at each of the steps in each iteration, I mean to say every iteration which we basically ask algorithm to follow. The random walk thus uses exploration approach while utilizing the search space. Now to better understand the concept of exploration approach and the iterated hill climbing algorithm, I will recommend you to watch the earlier lectures and more particularly I'll suggest you to watch the video lecture 21 of this series. Now let us try to understand the random walk algorithm. So random walk algorithm takes basically two arguments, so a starting point and number of iterations. Now this starting point perhaps might be the optional, because the reason is that you can ask a random walk algorithm to either start with the random candidate solution or you may explicitly ask the algorithm to start with certain specific node. So here the initial node is either taken from the candidate list of candidate solution or it can be a starting node. Now that node which we have selected as the initial node is the best node. So we'll start with the assumption, this algorithm basically starts with the assumption that the node selected as the initial point is the best node. Now for certain n number of iterations, it takes the initial node and it tries to get the information of child node of the current node. So here MOVEGEN function is called for the given node. And how MOVEGEN works? So let us focus on the sub algorithm of this random walk algorithm. So MOVEGEN will take a node. It will first search the node in the list of successors for the given problem. And if that node is available in the list of successor, it will extract the child node or children of the given node n or node and will return that list to the main algorithm that is called random walk algorithm. Now in child we have a list of the successors of the given node, and if child list is not empty, it may happen so that we may arrive with the nodes which doesn't have any child. That might be the leaf node. So in that case, here is the test that if the child node is not empty, then from that list of child, randomly select a node from that child list and take that as the node to be further explored. Now if the node at this point of time is having higher heuristic than the best node we have observed so far, then our best node will not be the earlier best node, rather it will be the current node which is having higher heuristic value. So this heuristic function takes a node and it returns the heuristic value of the given node. So here in this if statement, the heuristic function takes the node, it returns the heuristic value of that given node. Now here with this test, the heuristic of the the node with higher heuristic will be the best node. Now this best node is written after all the iterations of the for loop. Now to understand this algorithm practically, we will try to explore this algorithm using some example in the next slide. Now here is the practical execution of the algorithm with a given graph. Now let us focus on the graph which is specified here at the right side of this presentation, this particular slide. So let us focus where I am pointing now. So we have a graph with certain nodes, and this graph is completely a directed graph, and moreover this graph has node and associated heuristic value. So A is the node and phi is the associated heuristic value. Similarly, we have a node T, B, C, D, E and so on. So we'll explore this graph at the time of execution of this algorithm. So now here A has a child T, B and C. So it has 3 children. Similarly, T has 2 children, D and B. This way this graph is explored. Now this graph is basically used as the problem on which this random walk algorithm is to be executed. Now here to the random walk, initial starting point is a start node which is specified here as a node A, and the number of iterations are 4. So here the node, that is initial point, is A, and that initial point will be considered as the best node seen so far. Now our algorithm will iterate from 1 to 4. That means it will make a 4 iterations as n value is 4. Now it takes the initial starting point A as the node and will call MOVEGEN, so that MOVEGEN function will take node A as the node to be explored. Now let us focus on this graph. So A is the node for which it is given in the graph that there are 3 successors T, B and C with respect to heuristic values 11, 13 and 21. Now these nodes are basically written as the child list by MOVEGEN, and that is stored in child. And now here child list is not empty because child has 3 nodes T, B and C. Now the random function will select randomly the node from these 3 children T, B and C. So assume that it has selected T as the node. Now here in this if statement, the node which is T, the current node which is T, its heuristic value is compared with the best node which is A in our case at this point of time. So this is basically iteration 1, that is I equal to 1. So for this I equal to 1 iteration, so this node T heuristic is compared with node A heuristic, and if it is greater than that will be replaced, that best node will be replaced with this new node. So here in our case T has a higher heuristic as compared to the current best node A, because A has heuristic value 5 and T has heuristic value 11. So this is true, then our best node will be T. Now when I is 2, that is the second iteration of the for, again MOVEGEN is called for this current node which is nothing but a T, which is set in the earlier iteration, that is I equal to 1. Now here the MOVEGEN will take a node as a T and will extract the child node of this T. Now in this graph, let us focus here where I am pointing now. So T has 2 children D and B and D. So with respect to heuristic value 13 and 27. So that is written over here. Now child is not empty because child has 2 nodes B and D. So this condition is true. So this random function will select child a node from the child list and assume that it has randomly picked D as the node from the child. So that is assigned to the node, and again same thing is done here. The heuristic value of the node, which is current node, is compared with the best node seen so far, which is T in this case. So as D, which is having heuristic value 27, which is higher than the heuristic value of T, so this best node value is updated to D. Now for iteration I equal to 3, the current node is D and MOVEGEN function is called for this D. Now D has two children H and I with heuristic 101 and 99 respectively. Now here again child list is not empty because child list has two nodes H and I. So here the random function will pick randomly the nodes, randomly a node from the child, and which is nothing but H. So again the heuristic of H is compared with D. So H has heuristic value 101 and D has 27. So obviously H has higher heuristic than D. Our best node is updated to H. Now let us see the last iteration of this algorithm. Now here for I equal to 4, that is the last iteration because we have specified the number of iteration value n as 4. So here the current node is H, and for this current node a MOVEGEN function is called, and for this H MOVEGEN will return the child of H. Now here there is only one child for H, that is M, so it is returned. Child is not empty because at least one node is there in the child list, and as it is not empty then it will randomly pick a node from the child, and in our case as there is only one node in the child, so that is basically returned by the random function, and the current node will be M. Now the heuristic of current node is compared with the best node. The best node seen so far is H, and heuristic of H is 101, whereas the heuristic of M is 17. So this condition fails, so best node is not updated. But after this our algorithm will be terminated by returning the best node, and in this particular case the best node is H with heuristic 101. Now let us try to analyze the algorithm with respect to the graph which we have already used for the execution of random walk. So here this analysis is more generic and general, but in particular we'll try to understand this with respect to the graph which we have already used. So regarding completeness, the random walk guarantees the solution if randomly selected starting point lie in the global optimal region. For example, if this is the gradient, let us focus where I'm pointing here. If this is the gradient of the hill climbing, then a randomly selected point between these particular gradient or this region I call it as a global optimal region. So here in this region, if any point is selected, that will lead to the global optima. So assume in our case this basically 2 points, that is T and B. If we start with A, then T and B are the points which will lead to the global optima. In this particular case, in this graph, H is the point having highest heuristic value. So I assume that this H is the global optima. So any point selected from this 2, that is T and B, will lead to the global optima. So this way, if fortunately any of these point is selected by a random walk, then that will lead to the global optima. So here random walk algorithm is complete in nature. It also gives optimal solution. Obviously, if the selected starting points are lying in this region, that is global optimal region, then obviously it will give the optimal solution. Time complexity, if randomly selected point lies in the global optima region and the heuristic function is properly defined, then search will take linear time. Obviously, once suppose assume that the initial starting point was A, then randomly picked point is T, which is nothing but the child of A, and after that suppose randomly picked point is D, and again fortunately it selects H, then here to reach the global optima it takes the linear time. And regarding the space complexity, it is same, that if the randomly selected point is a point which leads to the global optima, then the path across that particular gradient will be a linear one, and so the space complexity is also linear. Hope you understood this random walk algorithm. Dear learner, how was the lecture? Please subscribe GCS Solutions, like the video if you really like it, share among the friends if you find it useful, and comment for the improvements. We are GCS Solutions, making technology easy to learn. Till next lecture, be intelligent.